Let me just set the stage a little bit today. We have my colleague here, Greg Schneider, works for Leica. He's going to really deliver the meat of our talk today. And what I guess about all I want to kick this off with as a point, because as some of you know, or maybe have a skeptical eye about, the amount of reality capture being employed in the building and construction market is increasing dramatically. In fact, I had a name here of one of my colleagues who I was going to pipe in, but he's so heavily embroiled right now. Our reality capture team is, has been on the road nonstop working with our client base. So what we see and hear, just yesterday we were talking with a construction company who's gone full tilt. They don't even want, we've had people that are service bureaus that do reality capture services that go out and scan jobs. This construction company has gone fully to the point of we don't want anybody on our site. We've taken this all on and we're doing it ourselves. And we hear from architecture firms who still say this is, it's too much. We don't know how to do this. The point cloud data is still too messy. It costs too much for us to work with this. So somewhere along that continuum, hopefully you are all somewhere along that continuum, and you've started to realize that the world of digital cameras, notepads, and tape measures is making you not as competitive as you could be for going out and capturing conditions, whether that's as-built conditions before you're working a job, or you're looking at quality checks after you've built a job and you want to scan and measure the as-built environment. So anyhow, I really just want to hand this over to Greg. He's got a lot to say. Just to give you a couple of quick resources here, there's a nice packet that Autodesk put out. This is about a 20-page PDF. I would have printed it, but saving on some ink, I suppose. I can put this document up in the meeting, I believe. I think I can leave this for you guys if you'd like. If this topic is interesting to you, I really encourage you to read this, because it should provide some food for thought. And looking at there's a page in this document that shows, hey, a flyover to do scanning today may cost you $40,000, but you can go buy a drone for $1,500, and even if you crash the thing, you're still ahead by quite a bit. So, the technology has come a long way. Greg was nice enough to pack his BLK 360 with him. And one quick note on that, because it's been the talk of the town. How many people go to AU here? I think ever since AU last year, our phones have been ringing off the hook. My colleague Bob Rice here in Seattle handles our AEC industry customers, has been pretty active in fielding calls about the Leica BLK 360. We did an event a couple of months ago, and that was, I think, pretty much every single email that came in said, hey, are you going to have the BLK at this event? And we did. And this is certainly a great piece of technology. It's arguably disruptive in the laser scanning space. Certainly encourage you to evaluate it and take a look at this to see if it's useful. I mean, the price point comparing the BLK to the professional series of scanners from Leica or other companies that create such hardware, it's a disruptive price point. So it's going to bring the barrier of entry to doing this down. However, know that there's still a continuum of technology that's available to you to do laser scanning. So with that, I'm going to leave it to Greg here, because he'll talk more specifically about the more granular details of scanning. I very much appreciate him coming out. Greg hails from Minnesota and has a long background in the survey and laser scanning arena, 15 years, I believe, something like that, upwards of that. So Greg Schneider from Leica Geosystems.
All right, thanks, Greg. I'm going to kind of take a slightly different approach to what we're going to talk about. I want to set some expectations for the different solutions that are available in reality capture so that you can kind of get your collective arms around what considerations do we need to make when we're looking at systems. And I like David's comment in the beginning, the point cloud really is your as-built model. Why model it? So we'll kind of take you down a road of educating you on some of that. My background is surveying. I started surveying in 1982 when I was just out of high school to make money to go to college, and then I've just stayed with the industry ever since. So I've got a long background in measuring capability and solutions. So this is kind of my agenda. I'll take you through some important topics of terrestrial laser scanning and what is it and what does it mean to you if you're going to incorporate any of the laser scanning solutions you're looking at. There's terrestrial laser scanner would be the traditional one you're thinking of, sets up on a tripod. And you're setting it on the ground essentially and scanning, but you don't leave it just on the ground. You're going to be mounting it in all sorts of different configurations. There are mobile solutions from backpacks to vehicle-mounted scanning solutions to now people are starting to play around with attaching them to a UAV and flying and doing, taking airborne LiDAR that we traditionally remember down to a smaller scale. But when you're looking for accurate information so that you're mitigating your risk in terms of your design and analysis, how do we mitigate that risk? And to mitigate that risk, you need to understand, set the expectations of accuracy, and what does all of that mean? So, one acknowledgement, a lot of the information in this presentation is supported by a presentation that was put on by Dr. Meghan Shilling with N.I.S.T, National Institute of Standards and Technology. So they take an important role in validating the capability of these measuring tools when it comes to different disciplines that are going to use them, more specifically like the forensic industry. Because there really is, one reason I do this presentation, there really is no set standards for us, the manufacturer, to produce a specification sheet, if you will, for our products. We all, when you look at a spec sheet or any marketing material, it's just that, it's marketing material to make your product look better than the next person's. So how do you drill down into the weeds and have a good understanding of what does a spec sheet mean to you, the end user? And I want to give you kind of some insights into that. So when you look at, there are two types of classifications of laser scanners. And essentially a laser scanner is a 3D camera that uses scanning or a laser beam to capture its picture, in its simple form. And then there's a survey grade laser scanner, which is going to combine that. It's going to be a 3D camera that uses a laser beam to measure, but it also has scientific engineering into it, scientific capability that meets the standards or level of accuracy that would be accepted by engineers and the surveying community. The true measurement professionals that are licensed to measure. And part of that will be, what is the capability inside of that instrument that allows that? So when you look at, laser scanner, they generate a point cloud and they capture an image. So, that's what they do. A point cloud is essentially a combination of X, Y, and Z coordinates. Instead of being, just a handful of those representing line work, it's millions of measurements that represent the 3D environment, the geospatial, world that you're building. You're building these beautiful BIMs from or to. A point cloud is just that, 3D representation. So when you look at a laser scanning imaging system, I'm used to having my presentation here. I go over and I look at my presentation. It's different to have a screen up high to kind of refer back to. So I won't be quite as animated today as I normally am. So when you look at a laser scanner, they're going to have a camera. Are they using an internal imaging system, which would be an onboard camera, or are they using an external camera that just simply is mounted on a tripod and captures that image after the instrument is done collecting its information? And one advantage to either is if you can get that focal point of that camera lens at the same axis point that your laser's fired, when you're looking at that image, there won't be any parallax. What you're looking at in that image is an exact representation of the measuring device. So, so that's really important. So if we're looking at this room, if we're measuring things from this viewpoint and our camera's looking at the same viewpoint, now we can trust what that image is showing us, and we can trust the measurements we're taking off of that image. And that's any separation from the source of measurement to the image is called parallax error. Parallax is going to be the error in your imagery to reality. So that's something to understand. We won't get into a lot of detail on that. But if your image is at the same source as you're measuring, you have no parallax, now you can trust the image that you're looking at. That's very important. Both scanning measurements are using a combination of information they're collecting when you're doing your scanning, and that's going to be what's your range. That's how far can it measure? What's the distance from the sensor? That's your range, and then you also have to take into account horizontal angle. So as we're firing that laser beam, and then we're going to move to our next measurement, what is the incremental error from that measurement to the next measurement? That's going to be our horizontal angle, and then we're also going to be, as we're measuring a very large dynamic field of view, we're also going to have a vertical angle that is important to determine the accuracy of that next 3D measurement that we take. So we're going to be measuring distance, we're going to be turning a series of horizontal angles, and we're also going to be measuring a series of vertical angles. That is very important to the overall accuracy of that single measurement that's taken. When you're measuring, some of these sensors will measure millions of points per second. So what is the relative accuracy of that single measurement? Because that single measurement's going to have a compounding effect on the rest of the measurements that you're taking from one setup to moving over to your next setup and so forth. We move on to our next setup, and then we're moving through a building, we're moving through a large geospatial area that we want to qualify our accuracy. All of that's compounding back to that single measurement. So that's something very important, and oftentimes gets overlooked. You get wooed by, oh, wow, look at that beautiful point cloud, but what does that mean from an accuracy standpoint? And then another component of that is the tilt compensation. So when we're set up and we're measuring, what is the orientation of all of our measurements to true gravity, the real world? When we hang a picture on the wall, we take a 4-foot level, we put that on the wall, our eyeball looks pretty good, we think that picture looks really good to our eye, but what is that relative to the real world? So it's very important in terms of those measurements, that geospatial accuracy to reality, you need to be properly compensated to gravity so that you have a frame of reference to all of those measurements you're doing in a building. So tilt compensation is done in several different methods. So when we put all of this together, we have our range measurement, we have our horizontal angle measurement, and then we have our vertical angular measurement. That all goes back to the sensor, and then we produce those points in 3D space. So all of that combined is our true 3D position as we measure. So range method, there are two types of scanning systems being used in the industry. Time of flight is what we call a pulsed laser scanner. So it's literally pulsing. It's shooting out a beam of light, timing how long it takes to leave the sensor, hit an object, and return back to the sensor. So it's pulsing. It's literally blinking that laser measurement. And then, very simple to do. What happens with time of flight is that fixed beam of light, it's kind of a conic beam of light, you can fix that laser spot size at a specific distance from the sensor so that you have something to relate the accuracy of that sensor. But with that fixed or focused beam of light, once it travels beyond the specified distance, that spot starts to grow very slowly over longer distances. So typically, a time-of-flight scanner can measure much more accurately further from its source than other sensors out there, other technology. Because when you're measuring any 3D space, right, we take a measurement on this wall, really doesn't matter how big that spot is because we can really see that beam of light very easily on a flat surface. It's when we start to measure more complex shapes that spot size becomes critical to our measurement accuracy, because as that light hits an object, it's going to elongate. It's going to change its shape based on how it's shining on that object, and that's going to affect the accuracy of where is the sensor back there at some distance from this spot. Where is it reading that light in true 3D space? Is it reading it on the right-hand side of it, left-hand side of it, or dead center? and that's going to affect that single point accuracy we're talking about. So time of flight is very good at that. Then there's another technology. Let's go here. It's phase shift scanning. And that's more like an EDM in a total station where it's emitting a continuous beam of laser light that has a specific ambiguity interval, meaning, and this gets a little bit beyond my education background and gets more really into the scientific world, but any light source has a specific wavelength to it. So when you're looking at phase shift technology, that beam of light is going to go out with a frequency, then it's going to travel a certain distance, so within that ambiguity interval, it can make a measurement because it's measuring along that line where it hits an object, and that's how it determines the distance. So then it reads that, goes back to the sensor, and maps that in 3D space. Challenge with that technology is, and it's all built on filters, it can't tell when it hits an object, depending on the wavelength of light, is there a measurement here on the true object? Is there an object in between that measurement and the source that's a potential position? And then if we take that light and double it, is there another spot that's twice that distance? And depending on the sophistication of that sensor, you're going to have 3 results for every measurement that you take in 3D space. And is it able to reconcile that in the reading back at the sensor? Oftentimes not. But what happens too with phase shift scanners and that technology, it's not so much a focused beam of light, but that light is going to go out, and when that spot reaches a sweet spot or the accurate distance that you specify, that spot's going to be what it is, but then it grows very, very quickly beyond that sweet spot on its measuring capability. So they're generally pretty accurate at shorter distances, but if they're measuring beyond that true accurate sweet spot, which might be 50 feet, these measurements back here, now you have a larger spot traveling through space. When it hits a flat wall or something, not so important, but if it starts to hit anything with shape, that larger spot is going to elongate. Now you have a bigger signature that's being recorded back at the sensor. And then again, you start to lose data quality, you lose positional accuracy of that measurement. So, the encoders on these instruments, you kind of break that down. They're using angular accuracy. Yeah. It kind of depends on your end use. Historically, phase-based scanners were much faster than time of flight, so they were really useful because you're measuring at shorter distances. If you're in a really congested area like a process plant or your line of sight is short, they're accurate within a much shorter distance. So their speed, but now there are sensors out there that are as fast as phase shift scanners, but they can measure time of flight, they can measure longer distances. So let me think of if there's any other information to add there. It kind of comes down to, I'll try to paint a picture for you to ask some good questions when you go through like a demo or you want to evaluate a sensor. There's more sophistication in time of flight. You tend to get crisper data than you do with a phase shift scanner, just in terms of the technology and the way it reads. So one of the things back at phase shift to kind of talk a little bit more about that ambiguity interval has nothing to do with how far it can measure. You might have a sensor that says, okay, we have 330 meter ambiguity interval range. All that's saying is that light's going to travel 330 meters before the signal repeats itself. So it could make a measurement within that 330 meters. It doesn't mean that it can see that light out at 330 meters. It just means that's the light wavelength signature of that instrument. So that's something important to know. We'll talk a little bit more about useful range a little bit later on too. It'll kind of help. Accuracy, you guys are all familiar with, seconds, minutes, angles, degrees. So when you look at angular accuracy with a scanner, if you're measuring in a very small step or very small angle, few seconds mean more accurate. The fewer the seconds means the more accurate your angular measurement is. So if you have an angle accuracy of 1.5 seconds, when you apply that to the real world, that's only about the size of a dime at 1.5 miles. That's terrifically accurate. So you're talking, you're not going to be measuring, a surveyor is going to be maybe measuring 1.5 miles, but now they use GPS for that, so they're not really turning angles, they're using other triangulation to improve the accuracy at these longer distances. But that's what 1.5 arc seconds equates to. So in determining, overall system accuracy is, your range noise is, and we'll talk a little bit more about what range noise is, but accuracy is the correct answer. We're trying to achieve the correct answer in our measuring. Precise means we can be very consistent about where we're trying to get our measurement. Accurate and precise means we're able to very consistently repeat the true measurement. And that's what we're all striving for. A lot of people say, well, it's accurate enough, but do you really try to hang your career on, well, I think we're working with data that's accurate enough. You always want to achieve, you're always trying to do the best job you can. And if you are and you do, you're going to sleep well at night. So what is range noise? I have that little asterisk up there, range noise. Range noise is just simply the repeatability of a distance measurement. How consistently can I measure a distance? And if you have very tight or accurate range noise, your repeatability in the distance, your data is going to be very clean. When you're looking at a measurement on an object, you're going to be able to see the detail of that measurement to that object. If you have poor range noise, now your data might be that fat, meaning measurements on an object are going to be, the repeatability is 1.5 or 2 inches. Now when you try to look at that defined edge like of a stairway, you're going to see this, these big fat lines that represent the stairs, and then you're going to step back and go, which of these areas of measurement is really the truth? It becomes very difficult for you in your design environment to have confidence in that data. And that's on hard surfaces. Now you start taking and getting complex shapes like architectural detail, some ornate crown molding or pipes or anything with shape that, that muddied point cloud makes it very hard to determine where steel beams are, structural beams, and all of that. So the range noise is the repeatability of a distance measurement. So field conditions also influence the accuracy of scanning. So when you're out on a job site, what's the stability of your tripod that you're setting up? Is there movement in that? Temperature is going to be changing a lot. You get out here where you have clouds that roll in off of the ocean and the intercoastal area. That's going to, the sun's going to go away. That's going to change the radiant heat that's shining on your instrument. That's going to have an effect on your accuracy of your measurement. You're always trying to mitigate that. Wind, is it windy out? How much wind movement is there on your sensor? Can it correct for that? Or can it read that amount? Vibration on your job site, are there compactors running, or is there harmonic vibration from generators and motors running on your structures that you're measuring in? And settling, there's all kinds of things. Bumping, did someone bump it and you notice that it got bumped? So now, like if you're running even your tape measure out and you're trying to get a nice long measurement with your tape, you're always kind of bumping it back to where you're measuring from, and then you're making your reading. Did somebody, did you make sure that it's still there and it moved? Now you read your tape, now you've got an error because you didn't notice that it pulled away from where you're pushing it back to. All of those are what's the source of my scanner from where the measurement's coming from. And then walking around, that's going to cause movement of your sensor. Can your instrument correlate that movement around the instrument to the measurements it's taking? And that's going to have an effect on the accuracy. So when you put tilt compensation is the fourth major system that determines overall positional accuracy. We've talked about the three, but then how does tilt compensation come into play? How level is our instrument? Can we sense any movement of that sensor while we're taking our critical measurements over a large geospatial area? Every little movement is going to have an effect on that. And when is that applied? If you are making that reading, when is that applied to the measurements that are actually collected from that sensor? So the ability to correct scan data to level. When is it out of level? tilting and by how much, and how much can we correct for that? And is there a correct reference to that movement during the scanning process? So essentially, out of level is out of level, very, very simple and straightforward, but you always want to kind of correct for that. So accuracy means, can we relate it, so how much movement, how small of a movement can we correct for? Again, this kind of goes back to that horizontal vertical angle. Tilt also is the same. 1.5 seconds of tilt is very accurate tilt. It's only going to be off, if we're off of 1.5 seconds of level, this is exaggerated, we're only off about the height of a dime at 1.5 miles. Terrifically accurate. If you're 54 seconds, now that's going to be multiplied by 54. That's how much tilt you're off at a longer distance. Well, now that's going to have a larger bearing on the accuracy of your measurements as you get closer into your sensor. So there's two different types. There's a liquid tilt compensator, and that's in high-end survey instruments, high-end total stations. We all learned in science as kids that water sits flat. It sits level to gravity. It's just the law of physics. With water, it's going to lay flat to the surface, right, or the area that you're working in. So terrifically accurate, and that's why we have the little liquid bubble vials in our 4-foot levels we use, because that's fluid. We have a bubble of air in there that's just going to ride perfectly flat to gravity as we move that. So there's that type. And then there's also tilt compensators that are electronic chips that are mounted on a glue board, like my cell phone has an electronic chip in it that will help determine how level things are. And this is based on just electromagnetic readings of the surrounding environment, and it's only as accurate as that chip is mounted on the board. So if you were to hang a picture on your wall, if you used your cell phone, you could probably kind of dial in, would you get it as level as if you had a nice 4-foot level in terms of determining what's flat? Which one would you guys use? So when they call these tilt compensators, they're actually an inclinometer. They're measuring an electronic incline of that chip, and then they correct back for it to gravity. So big difference. So when you look at a field workflow, breaking this down, if you're doing, let me see where we're going here with this guy. So we're always trying to mitigate our error in terms of the accuracy of our sensors. So some of the field work that's done with scanners is doing what you call registration, tying multiple scans together, and how do you accomplish that? One of the most common ways of doing that is using targets. So you're using some type of reference measurement in your overall scan scene to align your scans together. So to do that properly, you want to make sure that you have a minimum of 3 targets, because when you're looking at measuring in a large geospatial area, there's 6 degrees of freedom. We have our x-axis, we have our y-axis, and our z-axis. So we can slide on all 3 of those axes, plus we can rotate on all 3 of those axes. So that gives us 6 degrees of freedom. So when you're building your BIMs and building that beautiful orthogonal model of reality, when you're out measuring in reality, you need to anchor yourself to all of those degrees of freedom to come up with a true, accurate measurement in 3D space. So in order to level yourself, okay, we're going to set up here and scan, then we're going to move over here and scan. How do we align that scan to this scan? A common method is to use some type of a target. There's spherical targets, there's planar targets. You can stick targets on the wall. Well, what that does, that allows us to, okay, we measured that target or a shape on the wall from this setup. We could see that same one from that setup. Now we have a correlation from one setup to the other setup. So if you're doing that target-based, in order to lock down those 6 degrees of freedom, you need a minimum of 3 targets in your overlap area. And that can equate to a lot of extra work in the field and a lot of extra equipment that you have to use. Another method would be So if you imagine you throw tilt compensation in there, now you're set up here, you're using an electronic chip to measure it, if you're using fluid, you're going to be pretty good. But if you have error in your tilt sensor that you can't really quantify, you're going to start to, or actually going back here, I'm kind of going the wrong direction with this, is if you have all of your targets in a small overlap area, you can really develop a hinge, meaning all of your frame of reference tying your scans together are in one small area. That's going to tend to allow your data to be registered together, but it's going to allow it to kind of flex on that alignment of the targets. In order to do proper scanning, you really should have targets around in a good geometric shape is going to help anchor that data down. So if your targets are close together, you have that hinge, your data is going to start pulling away from reality. You're going to have your starting scans are going to be good, but all of your other corresponding scans can start to pull away from true level, true reality, because you have that hinge that they can move on. So your error accumulates, the more scans you do, and that could be, we're looking at a linear roadway example, but imagine we're going through a building, we're going that way, and then we're going that way, we're going up, and then we turn and we come this way through a doorway. Now we start going down, pretty soon our data is floating all over the place because we're basing it on, we're tying them all together on a hinge. So you have to try to do the right approach to mitigate that. So in order to improve that is you introduce some type of surveying work. Again, using an instrument that can truly measure gravity, and then from that, now you have a good frame of reference to the real world and how level you are moving through a job site. And then to do an acceptable project, you really should run like a traverse, do a closed traverse, survey through your targets, and that's going to improve that. Now you're introducing a lot of extra work in terms of your field workflow. So there's target-based, and then there's cloud-to-cloud registration that, again, is going to have all of the same error component, the error factors as using target, and that's where you're using the overlapping measurements, your point cloud, to do your alignment of the scans, where you're going to be, okay, we measure this, now we can see that wall in this scan, we can see that wall from our next scan. We can use that framework to do our registration. That's called cloud-to-cloud registration. And then there's different capabilities and different software tools out there and how they do that. So if you can imagine, we talked about range noise, and we've talked about whether you're level or not. So if your starting scan is out a little level, then you tie another cloud scan to it, your second scan is only going to be as accurate as the starting point of your first setup. That's the framework, that's what it's being controlled by, and that's going to continue to go. Yeah, question? It's going to vary based on the software solutions that are out there. A lot of them will do automatic cloud-to-cloud alignment. Sometimes you can do it manually if you want to, because it's having a challenge determining proper overlap in those scans. So there's different levels of tools and different software products out there that are going to do it in a different manner. So some of the software out there is actually trying to model objects in the point cloud, right? So now they're taking this scan, okay, we can see that beam from here. It's going to try to model an object on that object. And then when we move over to our next setup, it's going to see that same object. Is it seeing it from the same direction or not? It's going to model an object on that object, and then use like that line work. It'll solve, I don't have to walk all the way over, it'll solve a line for the edge of this table from scan 1 and scan 2. Now our cloud-to-cloud alignment, if you're modeling objects, is only as accurate as the ability of that software to model that object and then make that alignment based on that modeled object. So you just have to hope, okay, setup 1, all right, we modeled that, we moved over to setup 2, we modeled that line plus some other stuff. How well do those modeled objects fit the point cloud is going to determine how quickly we can align them and then how accurate they're going to align. So if we have that, remember we were talking about if we had inaccurate range noise or really fat data, where is that position of the line to reality as it makes that alignment? Some solutions will use, some software will use the true shape of the point cloud to do a least squares best fit alignment to the shape of that geospatial measurement, like in this auditorium. Use the shape of this auditorium to align them. It's not modeling any objects, and sometimes you get better results with that type of solution. So when you look at automated, your question about, how do they do that? Some are doing it automatically, modeling the objects, and then what are the relationships of those scans? You have to kind of educate the software, like the Recap 360 app. That will, systematically you're going in time, you're setting up here, then the next setup is right here. It's going to be very easily, it'll be able to make that relationship because we set up there, we moved to 2, and we just make sure we can see overlap. But if, say, we moved out of sequence, now we might throw a wrench into that registration process because it's kind of busy here, I can't get over and do this setup where I wanted to be. We leave the room and go out in the hallway and do another setup. Now there isn't any relationship from these 2 scans to that next scan. It might get confused trying to put it together. So you have tools in the software that allow you to make the proper correlations of the setups to do cloud-to-cloud registration. And then there's also doing kind of a mix where you do a hybrid approach where you do cloud-to-cloud plus targets to help constrain your scans together. Now, if you have other capability, you might be able to traverse with your scanner, where now you can set up on one point, backside a baseline, turn an angle and measure a distance to another control point. Now you can do your registration, turning angles and measuring distances just like you would with a survey instrument. That's going to streamline your work process and give you some checks in the field while you're doing your work. But again, that's only going to be as accurate as the sensor's ability to level itself, how accurate can it turn an angle and measure a distance. All of that is paramount to the overall results that you get. So when you look at, we were talking about tilt and the influence of movement on an instrument to the accuracy of that. Real-time liquid compensators, they're making readings on that during the scanning process. So every measurement that's being taken up to 1 million times per second is that light, that return signal is being reflected through the fluid that is telling it which way the up direction is, how level is that measurement. So now we have a high level of confidence of every measurement that's coming back and validate how level are we and how plumb or how vertical are these measurements to gravity. All of that's happening simultaneously. So in the end, we're going to have high confidence of that single point positional accuracy, that single measurement, but we're capturing 16 million points in a minute and a half. We're going to have a high level of confidence on that. When we were talking about the inclinometers in sensors, and that's the same for this sensor right here, it has a tilt, it has an inclinometer in it that measures, our horizontal, it measures its levelness to gravity through using electronic circuitry, but that's separate. So when we're scanning, it's going to scan, and then it's going to take a reading on that tilt sensor. It's a totally separate analysis of that setup. There's no correlation from the scan measurements to the tilt sensor, and then it's going to capture an image, and then it's going to read the tilt again at the end. So if that scanner doesn't move, you're okay, right? There's no influence of that list we talked about. There's no influence on it. We're fine because it hasn't moved, so that tilt reading will tell us the position it is in space. But now we're going to lose confidence in if it's windy out, that it's getting bucked around by the wind, or there's people walking around and we're on carpet or false work, framework, that scanner's moving, there's no correlation to that. It's going to apply a correction to those measurements whether we need it or not. Or we set it up, we scan, and before it reads the tilt sensor, somebody came by and kicked it, it bumped it, now it's moved from its source. Now it's going to make a correction to that. There's no correlation. That's all done back in the office. So when you get back in the office, some of those readings might be as much as 7 minutes after the measurement was taken. You get back to the office and you're going, I'm having trouble getting this to register. You're starting to see problems with your work process, and it just kind of accumulates. So there's some that do that, observations applied, and it's applied after the fact in the office, and it'll apply a correction whether it needs it or not. So there could be a difference, and that's going to have an effect to how you use that data downstream and how that data is corrected for as you move through your job site. You know, that can really compound the results that you're trying to achieve. So you just have to be mindful of being very careful about your field approach and talk to your manufacturer about them educating you on a good work process to help mitigate a lot of these in terms of your work. So, you know, start your scan process. You know, you can do some things to check it and test it and try it. The real big challenge is, because there is no correlation, it's not going to alert you if someone bumps your, you know, like if you're out by yourself and your tape goes up to that foot, we make our measurement. If there's not somebody standing there watching the end of your tape going, your tape moved, you don't know that, and you're reading it, okay, 167 inches and a half. You know, that's kind of the example. So this is really what can happen with your data when there is no correlation. Your instrument doesn't advise you that it's moved or it's not correcting for you properly. It can be as dramatic as that, because you can literally move it and there's no correlation. You want to have something that's going to be monitoring that for you and alert you if it moves. Yeah. That's managed by an IMU. So now you have another form of technology, like with UAVs, there's roll, pitch, and yaw. You know, that's rolling, roll, pitch, and yaw is rotating on your X, Y, and Z, moving on your Z axis. There's an IMU and there's centrifugal type of component that's monitoring that and correcting for that in real time. Some of that's done with GPS, you know, and airborne LiDAR. So we kind of review some of these factors. You know, we got our distance measurement, horizontal angle, vertical angle, and range noise is a critical component. So, you know, when you look at, you know, accuracy of, you know, why is scan data so accurate, it really just ties back into you're having your confidence in the data that you're working with. And it's, you know, having confidence in it is going to allow you to be confident in the decisions that you're making. It can give you confidence in the results you're reporting on your project, and you know, you'll sleep at night. So when you look at, you know, what are the different, you know, pre-construction, you know, accurate as-builts, and, you know, in your design work, you're trying to avoid rework. You know, you're trying to do your client and your company, you know, the best service you can. And it's, you know, it's expensive to move equipment and systems and have to retrofit things. You want to be able to have stuff fit up the first time and really know what you're working with. Construction validation, you know, right down to anchor bolts. You know, civil applications, you know, again, it really is kind of, it ties into all of the various vertical markets on, you know, the importance of data accuracy. And for forensic investigators, you don't want to have someone come in and you know, challenge your evidence that you have. Survey grade, you know, they qualify, you know, for scientific evidence. They've been admitted in the court of law. And then they're, you know, the Daubert standard requires a known potential error rate and being able to quantify that. So then, you know, here's some examples of, you know, looking at a time of flight versus a phase-based scanner. They both have an equal specification in terms of how far they can measure, but they're using two distinct technologies. So you might think, oh man, this particular instrument can measure 330 meters. That's what it says here in writing, but in reality, you get out to a job site like that, and you can't measure as far as you were told that it could measure. You know, it's real world information. So you really need to be mindful of what is your intended end use of your sensor and so forth. Test protocols, go outdoors on pavement, make sure you measure something that's part of your day-to-day work. What is your core work? And making sure that whatever instrument you're going to use can measure what's part of your core day-to-day work. And then maximum range versus useful range is scan density or resolution is seeing any object at a level of detail so that you can determine what it is in your design software, being able to visually see that level of detail. Is it sufficient at the range to see the detail of that object? Because that's really the power of scanning, is capturing a visual representation of reality. And then when you bring it back into the software you're using, is it maintaining that level of detail that you can see that from a design standpoint or model validation standpoint? But then, is it sufficient at these ranges to see that level of detail? The further away you go, every instrument's measuring radially, meaning the further away you are from the sensor, it's going to be stepping further across an object, which is going to reduce how often it's taking a measurement. And then there's various settings on those instruments to be able to increase your resolution the further away you are in the instrument from that setup, so that you can, you get full use out of that setup. Can I crank, okay, I'm scanning this room, but I need my critical area is that electronic control room up on the wall there. From this setup, what kind of setting do I need to be able to see the level of detail? I need to see the speakers and the vents that are coming out of that, and I need to be able to define where that glass is, because we're going to replace that glass. Can I see that with a level of detail here? Or can my sensor scan this, but then just focus in on that area to capture it at a level of detail that we can use effectively in Revit? And there's various capabilities of equipment. Or do I need to move up there then, do another setup closer to it so that I get the level of detail I need? And then how far, in order to do proper scanning, you should really work within the footprint of your targets. How are we going to register our scans together, position it onto gravity? So we really should work within the footprint of our targets as well. So how far can we acquire our targets we were talking about for doing target registration? And then what type of target do I need for the sensor? How large does it need to be for the sensor to see that? Because that's going to determine how much equipment we need to bring in the field with us to get the job done. That's important too. So when you look at range, we'll kind of blow through this, we'll kind of get caught up, and I'd like to open it up to some additional questions and things. How are we doing on time? Doing pretty well. So range performance, 300 meters, but I really can only acquire targets at a shorter distance. So we really are going to have to do additional setups across that distance in order to capture what we need and have targets in our overlap. So we need to be mindful of that. That's going to determine how long we spend in the field to scan. So here's an example of taking, if we had to map like this parking lot area, and we'd have to, we look at that, that's a tremendous amount of work to go out and work within the true specifications of that sensor. Now we're going to set up. Now, if we're moving this way, we have to have set up here. We have 3 targets here. We need 3 targets here, and then we're going to move and go that way. So now we'll have to have 3 targets there, 3 targets there. In what direction are we going to move? You need to have targets in that overlapping area at a distance that your sensor can read them. So that's just going to kind of compound the amount of work involved to do proper field work. And also, to maintain a level of accuracy when we get done, that we know when we're designing something that's going to go across that space. It could be a large warehouse. How accurate are we going all the way across that warehouse and looking up into the ceiling? Whereas if you have a sensor that has a longer range, a true useful range, and a true accuracy across that entire usable range, now you can really reduce the amount of field work involved to do that. Scan speed is really not that important to your total time in the field. Again, from that illustration, scan speed is one thing. How many measurements can we take in a second? It's going to really be quantified by how much work is involved to be able to take one setup, tie our setups together, be able to tie into our targets and all of that. And then, there's also, what kind of weather conditions can your sensor work in? That might limit your use. Like out here, if you're out on an exposed job site here in Seattle, you have a lot of rain. The number of days that you have precipitation is up there. Can your sensor really be used in inclement weather? Or do you have to take into account inclement weather and take precautions to protect that equipment? Can it be used out and exposed? Like this sensor has an exposed mirror, so it's really designed to work indoors. Because what's really important, we've been talking about horizontal angle, vertical angle, and range, and the accuracy of scanning. What's really important to the accuracy of scanning is this angle where the laser light comes off of the laser pump, hits that mirror, and is turned at 90 degrees. This angle right here, because where is that laser light in 3D space when it makes that bend from this sensor? This angle is very, very critical. If this mirror is perfectly clean, there's no dust on it, there's no moisture on it, we can make that angle very accurately. So when we're measuring out over its field of view, we're going to be able to trust the measurements that come from this sensor. If there's any, real important is if there's any moisture on that and dust, it's going to bend that light. So now that laser light bend, there's no way to quantify that change in angle. Where is that laser light going off in space? So if there's moisture on it, this thing is really a useless sensor, because where are we measuring in 3D space? So that's one of the single most, there's so many air components, but that's a really important aspect of scanning is having a protected mirror, something that's weather protected. So then, temperature range is going to affect, because each sensor is going to be affected by the temperature of our atmosphere. It's going to have an effect on the correction for that laser light measurement. Plus, it's also going to have an effect on, how much is this instrument changing at a given temperature? How much is this sensor changing its shape? How much is the tripod changing its shape at different temperatures? And what kind of temperatures can the laser pump effectively run is going to determine how useful the equipment is as well. So very important to understand that. And and then graph show the average temperature ranges. So you look at like Chicago, Illinois, for example. There's a lot of varying temperature ranges that are in different regions. Here you have a fairly stable temperature range. Compared to like where I am in Minnesota, we have some really dramatic changes in temperature, and we'll have days where it changes as much as 60 degrees in one day, if not higher than that. We can go from a nice sunny 70-degree day to 10 degrees or 5 below zero, and it's like, holy crap. But again, that's going to have an effect on the performance of your equipment, because when is the contractor going to say, okay, we need to go out and get this scanning work done? Well, you know what, we're kind of shut down because there's some rain, it's really cold out. That might be your window. Mother Nature isn't going to control when your schedule dictates when you have a window to get in and get the information that you need. So it's something to be mindful of. Can I use it in a wider variety? And make sure you inspect, when you look at any sensor, make sure you inspect the data that you're looking at. If you're looking at what your intended use is for that data, make sure that you evaluate the 3D data, not what you're looking at from the scanner. Everything's going to look really good from its source. Make sure that you rotate around and look at the true 3D data to look at the data quality that you might get from any sensor, because that's the information you're going to be looking at and using the 3D information inside of your Revit environment. So this is a bubble view. That looks really good. But then you look at the true data from the sensor. There might be waves in it, noise, all of the things we've been talking about. And then ambiguity points is what happens based on your laser spot size we were talking about. If you have a larger laser spot size, or like in the case of like a phase-based scanner, you're measuring at a distance that's beyond the real usable range of that instrument, because that laser spot size is getting larger, you'll start to get that effect where you call it ambiguity data or mixed pixels, where that light is starting to elongate. It'll start getting readings out here in space because that light is leaving that object. It sees that light out here in space as it goes off of that edge. You get a return out there, and then it's really hard to see detail fine detail on things because you have these points that are kind of stretching out into space. And then another example. So hopefully some of your takeaways will be, there are two types of laser scanners. You know, there's time of flight, there's also survey-grade laser scanners, and then there's phase shift or phase-based scanners, targets and survey control. Is that needed or not on projects? What's the useful range? And is more important, useful range is really more important than the maximum range of a sensor, because that's, you know, where is my data useful? And the IP rating of our scanner, scan data should be inspected carefully in 3D. So that's kind of an overview and kind of a nutshell educational presentation of scanning. And when you think about, you know, point clouds moving forward in Revit, I can show you some examples of, you know, the bandwidth of scan data. But there's capability out there of opening 2.5 billion points in Revit, efficiently loading in 1 second, and all of those points load in without affecting the performance of your Revit software, and doing clash detection, anti-clash in your Revit environment. Because a point cloud really isn't necessarily going to always show where you have problems. It can help you validate the integrity of your design as well, your BIM. You know, it's not always to point out problems, but it can help give you confidence that you know things are going well. And the point cloud is your model. You know, you don't, you know, say you need to go out and as-built an existing building, you already have the BIM done, it's constructed. Before they cover up the PT deck, you scan the PT deck, bring that point cloud in, you can validate the location of your PT cables before it's covered up. And if you have to make a slight adjustment, you don't have to build a model out of it. Just take your existing model and correct it slightly. You know, just move those modeled objects over. You'll be a lot more efficient in that point cloud, again, because there's different software products that allow you to work with the point cloud efficiently. You don't have to first turn it into a model to efficiently use it in your design environment. Yeah. Well, resolution is the level of detail. So, and that's going to be based on sample spacing. It's usually defined by a sample spacing or a measurement, an increment of measurement at a distance from a sensor. So that's essentially what resolution is how often. So if we need to see the level of detail of like this leg assembly here, we'd want to be taking a measurement at least a couple millimeters by a couple of millimeters across this area to see that level of detail. And that's usually expressed in a distance and then my sample spacing based on that distance. And then there's some sensors that have the ability to, you can measure a distance to that object and then you know how far away it is, and then you can set your sample spacing based on that distance from the sensor as well. There's varying degrees. Some then just have, like that just has a low, medium, and high resolution, meaning you don't have a lot of flexibility in terms of the level of detail you're capturing. But again, that's a pretty, you know, low-cost sensor, but that's how most of them operate, is you have a predefined resolution settings in it. Does that make sense? Yes. Yep. Yeah, so that's just, all that is when you're talking about that is, how often am I taking a measurement? It doesn't mean the quality of those measurements. That's just saying, okay, I can take a measurement, I can step every millimeter across that area at a given distance. It doesn't mean that I'm going to get that return in the proper location at that position. Because some will say, well, we have, how do they do it? They call it resolution accuracy, or range resolution accuracy of this. That's just meaning that we can step that often at that distance. Doesn't have anything to do with the 3D position, if that helps.
And that also be a function of the distance and the angular accuracy resolution of the scan itself.
Yes. Yep. Because, in 3D space, when is it making the reading of that angle? Is it able to read that angle real time, like a real-time dual axis compensator, or is it stepping and there's a time delay between when that angle is actually read to know where it is in 3D space. That is a limitation in sensors as well, but understanding that angular step accuracy too.
What's the performance issues for finding Revit models with the point cloud as far as the reduced performance?
I'm not sure. Let me-
Working back, model update. You use actually updating rather than lower resolution actually coming back up.
Well, lower resolution depends on the software. Software capability is going to load the point cloud faster. Certain software is going to require you to reduce the level of detail of the point cloud for it to open efficiently. And then can you see that correlation back to your model? Some software is going to allow you to load, it doesn't matter the size of the point cloud, so you can load that point cloud in a higher resolution so that you can validate your model. Is that what you're asking?
That parking lot, with all those changes, what would be my expected performance in that?
Your expected performance in Revit, again, depends on the software you're using. You should be able to load that point cloud in Revit, load it in a couple seconds, a second, and have all of that data available to use in real time inside of Revit.
Yeah, I can add a little bit to that. And we're also almost out of time, so I was going to suggest if there's any more questions, we can hang out for a little bit and answer them individually. But you know, I've manipulated rather large point clouds in Navisworks and Revit for a number of years now, and the technology has just gotten better and better. And sure, I've always used pretty beefy machines, pretty good hardware for it, but the latest, you know, the last version or two of Revit, the reality is that really large, like gigabyte plus data sets come in and file loads up. Typically, the refresh rate in Revit is going to suffer more because of your model elements than because of the point cloud. So I don't think that it's going to do something you're going to significantly notice. However, I would like to, first, Greg, thank you very much. This is very scientific, really great. Yeah.